In this lecture, we will see how to extend, at the cluster scale, the approach of optimization of renewable energy sources in the urban scenario. I will use photovoltaics as an example to clarify the concepts that will be discussed. But first, what is a building cluster? There are several available definitions which take in consideration different aspects, such as geographical limits or the type of use of the building. For this lecture, we can assume that the building cluster is a group of buildings in a limited geographic area that are connected to the same low-voltage distribution grid. To decarbonize our cities, we need to improve the sustainability of renewable energy projects. To achieve this goal, we can adopt optimization of the renewable energy sources at building level as shown in a previous lecture. However, we can also broaden the perspective to include more than one single building in the analysis. Here is where smart cities and energy communities can help us. But this is a different chapter. Let's go back to our topic, optimization at the cluster level. The idea in this lecture is to see what is the impact of including multiple buildings in the optimization process. From our point of view, the most important point of using the cluster scale is the advantage connected to the energy sharing. As we will see in the next slides, the possibility of sharing the energy production and consumption can help to improve the performances of the system that we are designing. Let's introduce the photovoltaic problem. We have a cluster and we want to find the optimal configuration of the system to cover part of the electric consumption, maximizing the economic outcome of the investment. We will compare two strategies, single building optimization and optimization at cluster level. Let's assume that in both cases we want to know how many photovoltaic modules we need, where to install them, and the optimal battery capacity. With the single building optimization strategy, we analyze one building at a time. This means that we consider the demand profile of each building and its surfaces available for the installation of photovoltaic module. Through an optimization algorithm or with an iterative approach, we find an optimal solution for each building. On the contrary, with the optimization at cluster level, we can aggregate the consumption demand and all the area available. In this case, we will not optimize the photovoltaic system one building at a time, but we will design a shared PV plant producing energy for all the buildings. What are the pros? In general, the single building approach works quite well for large buildings, with wide areas available for PV installation and with a quite smooth electric consumption profile. But let's assume that we want to analyze a cluster where buildings have different sizes and orientations. Some of the surfaces available for PV installation could be shaded in some periods due to the presence of near obstacles such as trees or other buildings. If we optimize the PV system at building level, some buildings will have modules installed on surfaces suffering shading or with not optimal orientations. Thus, they will produce less energy. They will have a lower energy and economic output. On the contrary, if we adopt the cluster scale, we can avoid shaded surfaces or not optimal exposures. For example, if some of the buildings have a limited number of well-exposed surfaces, with the cluster approach, we can find the optimal mix of different orientation to maximize the overall self-consumption. Moreover, during the design phase, it is not easy to guess the demand profile of the buildings under an analysis. Of course, the aggregated demand is smoother with respect to the individual demand, and thus, it is usually easier to approximate the electric consumption of the cluster. Another important point to keep in mind is that aggregation could decrease the initial cost if also the generation is shared. In fact, if the system is sufficiently large, it will be possible to buy PV modules at a lower price. Installation costs could be decreased thanks to the simplification at the logistics level, as well as maintenance costs during the year of operation. And even if the generation is not shared, the economic outcome of the community is usually higher. What is needed? Of course, to fully exploit the advantages seen in the previous slides, it is needed an infrastructure that allows the sharing of energy between buildings, while at the current status, buildings interface individually with the energy provider. Thus, the disadvantage is that an investment is needed to allow the buildings to exchange both energy and data, to adapt the local grid to accept groups of prosumers actively connected to the grid, and to allow the self-consumption of energy not produced in the same building. Finally, a review of the regulations regarding renewable energy sources installations, energy sharing, and the interaction with the grid is essential to regulate and renovate all the aspects connected to safety, privacy, and to introduce new business models. So, optimization at the cluster scale has several advantages. Thanks to the increased area availability for PV installation and the aggregation of the consumption demand, the designer has a greater chance to design the optimal system for maximizing the energy and economic outcome of the plant. Moreover, initial and operational costs could be decreased. To fully exploit the advantages seen, some investment is required. However, in the last years, there is a positive trend related to the activities in the field of energy sharing and energy communities. In 2020, energy sharing is not the standard scheme in the urban context, but in the next year, we hope to see an increase of real application. I would like to conclude highlighting the importance of the sustainability of renewable energy projects, which is essential for the energy transition that the world is facing. That said, designers could play a relevant role in the decarbonization of the building sector, and they are expected to be ready to face even more complex and challenging design problems, including also the interaction with other buildings of the same cluster.